Welcome back. In this module, we discuss how the internet and networks actually work. We talk about IP addresses, DNS ports, and traffic flow. Cybersecurity discussions often assume that everyone shares a basic understanding of how the internet works. Terms like IP address, DNS, ports, and network traffic are used casually as if their meaning is obvious. For many professionals, they're not. That gap matters. You do not need to become a network engineer to understand cyber risk, but you do need a clear mental picture of how information actually moves across digital systems, how devices find each other, how communication is routed, and where exposure quietly appears. Almost every cyber incident, regardless of industry or attack type, relies on these same underlying mechanics. When those mechanics are misunderstood, risk becomes invisible. This section is about making the invisible visible. The internet is not the cloud, it is a network of networks. The internet is often spoken about as if it were a single place, somewhere out there where data lives. In reality, the internet is not a location at all. It is a vast, decentralized network made up of countless smaller networks, each operated by different organizations, service providers, governments, and infrastructure owners. When your device communicates with another system, your data does not travel along a single owned pathway. It passes through multiple independent networks, routers, and transit points. Each of these components makes local decisions about where traffic should go next. This design is intentional. The internet was built to be resilient. If one route fails, traffic can be redirected through another. If one network goes down, others continue operating. No single entity controls the entire system. From a cybersecurity perspective, this resilience comes with a trade off. Because no one controls the full path, no one has full visibility or authority over it either. Data moves through environments you do not own, manage, or directly secure. Security, therefore, cannot rely on ownership alone. It must rely on assumptions and controls that compensate for those assumptions. IP addresses, digital locations, and not digital identities. At the most fundamental level, communication on the internet relies on IP addresses. An IP address is a numerical label assigned to a device or system that allows it to be located on a network. You can think of it as a routing address, similar to a mailing address, but with an important distinction. An IP address tells the network where to find or send data. It does not tell you who is using the system. IP addresses are not stable identities. They can change over time. They can be shared by multiple devices. They can be masked, hidden, or translated. Entire organizations may appear to the outside world as a single address. This distinction is critical for understanding cyber risk. Attackers rarely need to know who you are as a person. They need to know where a system is reachable. IP addressing enables that reachability. It is a location mechanism, not a trust mechanism. Confusing the two leads to false assumptions about security. Public and private IP addresses, visibility and exposure. Not all IP addresses are visible to the internet. Many devices operate behind private IP addresses, meaning they can communicate internally within a local network but cannot be reached directly from the public internet. A gateway device, such as a router or firewall, sits at the boundary translating traffic between private systems and public networks. This architecture is everywhere in homes, offices, data centers, and cloud environments. From a security standpoint, private addressing creates a layer of separation. Systems behind private IPs are not directly exposed to unsolicited traffic from the internet. But this separation is often misunderstood as protection. Private addressing reduces exposure. It does not eliminate risk. Remote access services, misconfigured gateways, cloud settings, or compromised intermediary systems can still expose internal systems. Boundaries help, but they are porous by design. Cybersecurity begins with understanding where those boundaries actually exist. DNS, how human friendly names become network locations. Humans do not navigate the internet using IP addresses. We use names. When you type a website name into a browser or click a link, your system relies on the domain name system or DNS to translate that human readable name into a numerical IP address. DNS functions like the Internet's directory service. It maps names to locations so that humans do not have to remember numbers. This translation happens automatically and invisibly, often in milliseconds. From a cybersecurity perspective, DNS is one of the most important and most trusted components of internet communication. If DNS responses are accurate, traffic goes where it should. If they are manipulated, traffic can be silently redirected to unintended destinations without the user realizing anything is wrong. Many cyber attacks exploit this trust. Why DNS is a high value target? DNS was designed in an era when efficiency and reliability mattered more than security. As a result, it assumes a level of trust that no longer reflects today's threat environment. Attackers target DNS because it allows them to influence where traffic goes without breaking into systems directly. By spoofing, poisoning, or redirecting DNS responses, they can impersonate legitimate services, intercept communications, redirect users to malicious infrastructure, all while preserving the appearance of normal operation. If you trust the name, you trust the destination. Understanding this helps explain why modern security controls often focus on monitoring, validating, and restricting DNS behavior. DNS is not just infrastructure, it is a trust mechanism. Ports, multiple services, one address. An IP address identifies a system, but systems do not provide a single service. A single device may host websites, email services, file transfers, remote access tools, and APIs all simultaneously. Ports are what makes this possible. Ports are numerical identifiers that allow multiple communication systems or streams to coexist on the same IP address. Each service listens on a specific port, waiting for requests. You can think of an IP address as a building and ports as individual doors. Some doors are meant to be open, others are meant to be closed. From a cybersecurity standpoint, every open port matters. Why open ports creates attack surface. Open ports expose services. Exposed services can contain vulnerabilities, misconfigurations, weak authentication, or outdated software. Attackers do not need to guess where those services are. They scan continuously. Port scanning is one of the most common reconnaissance activities on the internet. It is automated, fast, and relentless. Any service exposed unnecessarily becomes part of the global attack surface, regardless of whether it is actively used. This is why reducing exposed services is such a foundational security principle. If something does not need to be reachable, it should not be reachable. Traffic flow, how data actually moves across the internet. When data is transmitted over the internet, it does not move as a single stream. It is broken into small units called packets. Each packet contains a source address, a destination address, instructions for reassembly, and a fragment of the data. These packets may take different paths across the network. They may arrive out of order, some may be delayed, others may be dropped and retransmitted. The receiving system reassembles them. This packet-based design makes the internet resilient, but it also makes visibility incomplete. No single point sees the entire conversation. Security systems must infer intent and behavior from partial observations. This is why cybersecurity often deals in probabilities, patterns, and anomalies rather than certainty. Stateless communication and implicit trust. Many internet protocols are stateless. Systems respond to requests without maintaining long term memory of prior interactions. This design favors scalability. It also assumes benign behavior unless proven otherwise. Attackers exploit this assumption. They impersonate systems, they replay requests, they flood services, and they exploit the fact that protocols were designed for openness, not hostility. Many modern security controls exist specifically to compensate for these original design assumptions. What firewalls actually do? Firewalls are often described as walls or barriers. In reality, they are decision systems. A firewall evaluates traffic based on rules, where it comes from, where it is going, which ports are involved, and sometimes what the traffic contains. If traffic matches allowed patterns, it passes. If not, it is blocked. Firewalls do not understand intent, they enforce policy. Their effectiveness depends entirely on the assumptions behind the rules, the accuracy of configuration, the completeness of coverage, and firewalls reduce exposure. They do not guarantee safety. Why internal networks are not automatically safe? A common misconception is that traffic inside an organization's network is inherently trustworthy. In practice, many breaches escalate precisely because internal communication is more permissive than external access. Once an attacker gains a foothold, movement within the network becomes easier. This is why modern security models increasingly emphasize segmentation and least privilege even internally. Trust boundaries matter everywhere. Why these fundamentals matter? Every cyber attack relies on these mechanics. Phishing delivers traffic, malware communicates over networks, exfiltration moves data, command systems rely on ports and routing. And when you understand these fundamentals, cyber incidents stop feeling mysterious. You begin to see why exposure exists, why attackers scan constantly, and why misconfigurations are so dangerous. Cybersecurity stops feeling abstract and starts feeling structural. The key takeaway is that the internet was not designed as a hostile environment. It was designed to connect. Security exists to compensate for that design, not to replace it. Understanding IP addresses, DNS, ports, and traffic flow does not make you technical. It makes you situationally aware. That awareness is foundational.